My name is Aryaman Sinha-17EE01016, and let's start with the question definition. What is the question? We have been given a PPG signal with a baseline trip up to the 0.5 Hz and a power line interference which gives a multiple of 50 Hz, and instrumentation noise which can be greater than 20 Hz. So basically, we have to filter out the PPG signal first from 0.5 Hz to 5 Hz, as the PPG signal range is dead. So we will just use the IR filter approach of Butterworth approximation, in which I've taken the first order only for the simpleness, and we will just use a BLT transform to use the analog to digital domain transform. And here passband H frequency lower is 0.5 Hz and upper is 5 Hz, and sampling frequency has become as 100 Hz. We will use the low pass filter to high pass band pass filter transformation methodology of S square plus omega naught square S omega into P, where omega P is the bandwidth of the proposed filter. We will just use that methodology to find the h of z and get the values of the coefficients from the transfer function proposed. We can use that coefficients to get the filter output using a MATLAB function or the Arduino code if possible. Uh, Basically, after that we will have to do the Arduino code programming, or we can do it in MATLAB also, using which you have to find the pulse rate of the patient. So pulse rate of the patient. So basically, two methods that have been proposed here. That are proposed. First is a autocorrelation function, and then the DFT or FFT1. In autocorrelation function, first we will find the autocorrelation function after doing a moving average, as we want just other noises to be attenuated. And zero crossing after getting the autocorrelation function, we will find the zero crossing of that points, first zero crossing point, and we will get L max, or the second peak index. And as we know, in the autocorrelation function, the second peak to the first peak, that distance will be the time period of the signal or the autocorrelation function as per the property. So we will just use L max divided by Fs for that to get the period, and to convert into a second to minutes, we will just multiply it to the 60, and we will get the pulse rate value, that is 60 pulse rate period, pulse period. And second approach is using a moving average filter to smoothen out the signal, then using a DFT or FFT, in which we will get the spectrum in which it will be symmetric. So we will just detect the first major peak point to max peak point, and use that frequency value, which is Kmax into Fs divided by N, and 60 is multiplied here because of the second to minute conversion, and that frequency will always be the pulse rate value of the patient. So after this is the code we have coded here. So x of n is the recovered signal we have got from the h of n, and n is the number of samples we want digital values to. Suppose we can take 2408 2048, and then first we will apply the filter to the MAF function, which is this one, in which we have taken the window function of 8, and just use the basic MF transfer function, which is just shifting and multiplying it with the shifted original function, and normalized it with the value of the n, which is basically the what function tell us. And then we will just use that filtered output and mean normalized it, so that it will be mean normalized, and it will be easy to calculate the autocorrelation function so in autocorrelation function, we have to calculate the R0, that is the energy function, which is x into x only, and summation from I is equals to 1 to n, which is in the for loop. And second, after that we will find the autocorrelation normalized function, which will be divided by R0 we have calculated above, which is nothing but the autocorrelation function is nothing but the shifted multiplication of that original signal, which will be j plus I, and we will use the windows of n minus I to just multiply it with the original signal, and by this we can get the autocorrelation function, normalized autocorrelation function. After that we will just found the first zero crossing point. After getting a first zero crossing point, for getting a first zero crossing point, we have just to check out the that the left point and right point should be of opposite polarity. Basically, the left point should be positive and right point should be negative. Then we will get the fuzzy crossing point. I will show you in the graphs it how it will be. So wait for a minute, and then we have used the we have used the autocorrelation function from fuzzy crossing point, and then found the second highest peak, which is L here, and index is L here. And for calculating a pulse rate, as we've discussed, will be the 60 divided by pulse period, which will be L divided by Fs. So we can just print that value in the void loop, which will be printed again and again. If you want to, you can do it outside the loop. Then in flowchart depicts the same methodology. We propose the bandpass filter, moving average filter, automation function for zero crossing point calculation, then Lmax finding, and after that pulse rate value. So in this we have just coded for the autocorrelation function. We can code for the DFT also or FFT also, and use that second approach to find the peak in the spectrum. So what basically I'm telling you, let me show you. So in this we have a rough sketch of PPG signal which will be symmetric in the TFT domain. The first peak point will be the here in DFT, so we will get the frequency of that peak point and just multiply it to the 60. We can use this from the DFT or FFT. FFT will be more or less complex, as it has of and log n complexity. Then we will in ACF the second peak is this point. As first zero crossing point we will get from this, and after that we can get the Lmax point, and for function we can get the pulse period. And we are using the pulse rate measurement in COVID-19 because we can use the proper evaluation by the doctors. They have to check again and again for the pulse rate. And for performance validation, we can just check out the pulse rate value should be in the minimum range. We are in the permissible range of the human range, and the spectrum should be liable like that. The time domain function should be as depicted here. So this is a PPG rough PPG signal. It should be look like. So thank you. This is all.